Hello everyone, welcome back again in the course of higher surveying, and today we are in the new module, module 5, Global Positioning System. Today you might be excited also because we are going to talk about GPS, which is a first relevant, at least you are feeling that it is a relevant topic. And before whatever we have covered, for example, the module 1, module 2, which was about reference frame and coordinate system, module 3 about astronomy and time, and module 4 about the adjustments computation and error propagation, accuracy, error, precision, and anything like that. You might be feeling that, or might be asking also, that why did we cover 4 modules, almost 14 to 15 lectures before we start today's lecture? Okay, let me tell you very clearly and categorically. First 3 modules or 4 modules are the basic fundamental tools, or they are the relevant concepts without which you cannot work or you cannot understand any topic of higher surveying. For example, if I take the module 2 about reference system and coordinate system, reference systems are very useful to understand what is geocentric coordinate system, or what is a geodetic coordinate system, what is a local reference frame, and so on. Later, we have also talked about astronomy and time. That is a part of the higher surveying, although today it is not very much relevant, but still it is part of the courses on higher surveying in different universities, colleges, and institutes. Okay, there we have talked about the time, like how to measure the time, what do you mean by time, what is atomic clock, what is atomic time, ephemeris time, what is rotational time of Earth, and so on. And we also defined something called sidereal time, that is related to the orbit as well as spin time of Earth together. Then we talked about astronomy, where we find out how to find the coordinate of the star or any celestial body. For example, it could be a satellite, artificial satellite. So we said that let us locate the 2D position of a star globally, locally. Locally we have said azimuth and altitude. Globally we have said declination and right ascension, and so on. And that's the reason we have said finally what is the ICRF, that is International Celestial Reference Frame. And then we have established the relationship between the ITRF and the ICRF. Remember that ITRF we learned about in the module 2 in the reference frame and coordinate system. ICRF we learned about in module 3 in time and astronomy. In module 4 we talked about what is accuracy, precision, what are the measures of accuracy and precision, and how to do adjustment computations to find out the errors and accuracy, and how to do error propagation to find out the precision in the propagated variable or the connected variables. Knowingly that we have some measured precision or estimated precision for some measurements in field, how can we find out the precision if there is a connected variable which is a dependent variable? Now, with this all thing, how to use these knowledge or how to use these logic concepts in today's lecture? Let us see, and you will appreciate really now from this point onwards that whatever tool we have learned in last 4 modules, they are very, very useful for development of your concepts about GPS and other technologies like photogrammetry, radar, lidar, bathymetry, and so on. Okay, so let us dive into today's lecture, and it has only one lecture, that is Global Positioning System, like this. And I should have coined this term as GNSS, which is Global Navigation Satellite Systems, because GPS is the term generally used for Navistar satellite configuration. What is that? Navstar or GLONASS or Galileo, what is that? We are going to discuss today everything. Moreover, this module or this lecture, which is, there is only one lecture in this module, it is more about the information that you perhaps need, but you are not aware of that. And that is the reason we are taking this GPS. I would like to confirm here one thing. If you want a detailed knowledge or the basic fundamental knowledge of the GPS, please refer NPTEL course on basic surveying, that is the surveying course. There they have, authors have, or the instructor have elaborately talked about GPS for 5 to 6 lectures. And those fundamentals are relevant as well as applicable here also. So I am assuming that these are the prerequisites for this module or for this lecture. So with this idea, I am going ahead now. Okay, so these are the books. I can say that these 3 books are fundamentals books, okay, and there also, this is slightly different book. It has slightly different taste or different flavor on the material, but still it's a relevant book. These 2 books are on the more on technical side. So if you are electrical engineer interested in the mathematical treatment of the signals and all this thing, you can refer these 2 books, but first 4 books are good enough for the any serious learner from the civil engineering perspective. That means topographic mapping only. Okay, here I would like to say this is the fundamental books are basically Hoffman, Wellenhoff here, and Kaplan's book is also good one. Rabbani's book, fine. You will get different ideas, different notations, different kind of explanations. So better if you can read these books at least one by one. Moreover, if you find these books expensive, always go to the basic surveying course on NPTEL, and the lectures which are about GPS are very relevant and appropriate. Fine. Let us go ahead. Now we have satellite orbits. So in general, satellites are placed in 3 types of orbits, and then we name them accordingly. So first is low Earth orbit, or in bracket it is written LEO, right? If you just try to see sometimes in the sky, and by accident if you come to know that there is a star which is continuously moving in the sky, perhaps it could be a satellite. If a star which is continuously moving in the sky, if you see it in one day, probably it is a LEO satellite. Moreover, please differentiate between aeroplane, which is quite big, that appears quite big to you compared to the star. A star appears like a dot in the sky. So if you are seeing that there is a dot moving in the sky in the night time, perhaps you are looking at a LEO satellite. You can see with the naked eyes. Okay, all the spy satellites, for example, Corona satellite program or Lanyard or Argon, all these early spy satellite programs, they were using LEO orbits, and the range of the LEO orbits is less than 1000 kilometers above the surface of Earth. So for example, Corona was placed around 150 to 215 or 225 kilometer range orbits. The satellites were orbiting like that, and they were acquiring panoramic images on the surface of Earth. Okay, later on when remote sensing was started, so nowadays remote sensing satellites are placed somewhere around 750 to 900 kilometer range. So they are also LEO orbits. Okay, all the weather satellites, generally if you look at the weather satellites reporting the weather, they are also placed in the LEO orbits. Okay, next is the MEO satellites, or the medium Earth orbit, and the orbit is around 22,000 kilometers above the surface of Earth. Well, most of the GNSS, again, what is the GNSS? Global Navigation Satellite. I can write here small term, Global Navigation Satellite Systems. GNSS is a generic term that includes all the possible satellite constellations. Well, GPS is, or Navistar is one of the satellite constellation launched by the USA or developed by the USA, and now it is in the working position. Well, apart from that, most of the countries developed and as well as developing like India, they have also developed their own satellite constellation so as to serve their nation locally. Their interests are more on their particular country. We will see all these things, but I would like to say here, most of the GNSS satellites are placed in the MEO orbits. Okay, these orbits are inclined with respect to the equator of the Earth, like this, or could be like this, could be like this, or could be like this. Okay, and orbital period defined in sidereal days. That means how many sidereal days a satellite is taking to complete the rotation or to complete the orbit around Earth, not rotation, revolution around the Earth. Well, then we have third type of orbits, called geosynchronous Earth orbit, we call it GSO, and geostationary Earth orbit called GEO. Okay, let me differentiate between the two, GSO and GEO orbits. GEO is geostationary Earth orbit. They are generally placed on the equator. That means in the equatorial plane at this height of 35,000 to 36,000 distance from the surface of Earth, they are revolving or orbiting around the Sun. So let us say this is my equatorial plane of the Earth. So somewhere it is 35,000 distance, and now satellite is orbiting in this plane of equator or equatorial plane, or you can say celestial equator plane. So these are called geosatellites or it's called geo orbit. Fine. Generally they rotate or they revolve around the Earth in the same direction of the Earth's rotation, that is anticlockwise. Well, then we have geosynchronous Earth orbit. You will be surprised that if I place the same orbit at 35,000 height above the surface of Earth, and in this inclined plane like this, or it could be like this, and let us say this is equatorial plane. So these orbits are called geosynchronous orbits. So what is the purpose of geosynchronous or geostationary Earth orbit? Well, these satellites which are placed at almost 35,000 kilometer height, they remain fixed with the Earth. That means when they are projected or when they are placed at a certain point with respect to Earth, then they will remain over that always. Why? Because they are rotating with the speed of the Earth, which means they are completing their one revolution or one orbit around Earth in one sidereal day. And that is why they are called synchronizing with the Earth, geosynchronous satellites, or geostationary. They remain stationary with respect to the Earth. But geostationary are placed in the equatorial plane, geosynchronous are placed in the some inclined plane. So we have two kind of now satellites, geosynchronous, geostationary. Remember, both revolve around the Earth with the same speed of the Earth, and that is why they are named geostationary or geosynchronous. Okay. Well, all the communication satellites, like for example that used for the mobile phones or TV satellites, television, they are placed in the geostationary orbit, right? And some of the GNSS satellites are placed in the geosynchronous orbits also, as well as geo orbits also, both. We will see. Let us go ahead. Okay, let us see. This is my one orbit here, fine. And now I can say here, this is the inclination of orbit. Now I am trying to define what do you mean by an orbit or orbital plane of satellite. You can see here the capital XYZ is a geocentric reference frame. Generally this capital XYZ is ITRF, International Terrestrial Reference Frame. Secondly, we associate with this reference frame a ellipsoid. For example, for GPS we associate WGS84 ellipsoid, right. So the moment there is a association of the two, one is reference frame which is geocentric in nature, and then we have ellipsoid. So I got a datum surface with respect to which I can refer the heights, what we call ellipsoidal heights. So I will use that ellipsoid for measuring the ellipsoidal height, and GPS is going to use that particular ellipsoid in order to report the ellipsoidal heights, right. So that's the purpose here, to associate two things. Now this is the one of the orbit of the satellite here, shown here, fine. So this is the inclination angle what we have seen here. So now I can see that all the satellites are moving, let us say, in this orbit. For example, like this, there are 4 satellites are shown that are moving in this orbit, and so they are maintaining some speed, and as a result they are not colliding with each other, rather they are moving at a constant speed with each other. And what's the order of the speed? The order of the speed of satellite is in the kilometers per second, right. Okay. Now with this idea, you can now imagine that for these 4 satellites, this is the one orbital plane, and rather these 4 satellites are assigned to this particular orbit, and they are moving always in this orbit, right. Let us go ahead. Let us take another orbit. This is another orbit, and what is the inclination of this orbit? So, if I measure the angle of this orbit with the equator, that is called inclination. So, let us see. This is the angle I for this orbit, because it is inclined with respect to the equatorial plane by this angle I. So, that is called inclination. Now, you can imagine there are two orbits like this, right? It could be another orbit like this, it could be another orbit like this, fine. So, you can imagine now that at a given inclination I angle, I can have these many orbits, which are, let us say this is orbit. So, this can be this orbit, orbital plane like this can be this way also, this can be this also like this, and this can be this also like this orbital plane. So, basically this orbital plane is making an angle I with respect to the equatorial plane, and that is why all these are different orbits although, but they are having the same inclination, right. So, now let us place like this. There are 4 satellites placed in the particular orbit having inclination I. Okay. Let us go ahead. Now, have you ever thought of a problem that how a coordinate of satellites are available to us? Because if you can recall the fundamental concepts of the GPS from the basic surveying course, then you will realize one thing, that we need to first have the coordinate xyz of satellite. Using that coordinate xyz, we try to find out the receiver's coordinate xyz. And what do we do? Basically, we have this xyz available to us, then we measure the distance by the time difference or maybe phase difference logic between the receiver and the satellite, and then we using this two information which is known, for example distance and the coordinate of the satellites, we try to find out the location of the receiver by some logic called space resection. Well, that was the idea we have already discussed, or you have already learned in the basic surveying, right. So, we assume that satellite coordinates xyz are available in some geocentric coordinate system. So, let us say that my geocentric coordinate system is xyz. It could be ITRF or it could be any other, does not matter. But for the purpose of concept, let us assume it is ITRF or it can be other, right. Then we have a orbit shown here, and what are the characteristics of the orbit that remain same for all the satellites moving in that same orbit, that we try to learn now. So, let us see this is a satellite here, and this point, if I connect the center of the earth to this point where it is intersecting, the orbit intersecting with the equatorial plane, we call it node, right. Now, if you say this is the angle inclination as explained in the previous slide, okay, then this is my inclination of orbit I, that is already marked in the slide. Okay, what next? Next thing is that this blue line here indicating, this blue line is the semi-major axis small a, right. So, this is my semi-major axis, fine. Okay. Since this node point is fixed for a given satellite orbit and equatorial plane, right, we can define this angle omega, that is the angle between this line which is connecting the center of the earth to the node and the line called semi-major axis. So, this angle omega is defined in the orbital plane. So, this angle omega is defined in the orbital plane of satellite, fine. So, now you can understand this is called argument of perigee. Remember what is the meaning of perigee? Perigee is the point on the orbit which is nearest to the earth, right, because this is the satellite of the earth. So, we are defining like that. Remember that earth itself is a satellite or the planet of the sun. So, we define perigee and apogee for the earth when we talked about the rotation of the earth and the orbit of the earth around sun. So, when we talked about the orbit of the earth around sun, we defined apogee and perigee points for the earth. Similarly, we are defining here perigee point for the satellite which is revolving around the earth. So, this is my orbital plane where it is supposed to revolve. where it is supposed to revolve around the Earth. Now, this angle, that is called the right ascension of ascending node. So, this node is ascending node because satellites will be ascending from this node and up. It will come in the northern hemisphere, right. So, now you can see here, this is called right ascension of ascending node. Remember, we have also defined the ascending node for the sun in the apparent path of sun, and that we call vernal equinox. Okay. And through the vernal equinox, we are saying that Greenwich meridian was passing to define the terrestrial meridian and terrestrial longitude and latitude and so on. So, now we are saying here x-axis, remember we define the Greenwich meridian, x-axis and everything. We are saying it is not relevant that it passes through Greenwich meridian or vernal equinox, rather it is passing through the 0° longitude, which we have decided based on the average rotation axis and all the average values, or basically it is a ITRF system. So, ITRF is giving me the 0° longitude by x-axis. So, that is why we are measuring the right ascension of the node like this. Okay. Let us go ahead. Now, this is the satellite and this is now the coordinate system small x, y, z like this, and this small x, y, z is an orbital plane. That means x and y are aligned with the orbital plane, or they are in the orbital plane, and as a result, now you can see that z axis, which is small z shown in purple color here, it is perpendicular to the orbital plane, and that is the reason somehow we have some facility here. What? Let us look into that. Let us look into the motion of the satellite, which is moving in the orbital plane. So, now you can see that since satellite is moving in the orbital plane, it is changing its coordinate in the orbital plane, but the z coordinate is 0 because my small xy coordinate system is defined in the orbital plane. Now, you can easily imagine that if I measure the time, so with respect to time, satellite is changing its position only in the orbital plane, right. So, I can always define the position in the 2 dimension. I need not to define in 3 dimension because the small z, the z dimension of the satellite in orbital plane, or with respect to orbital plane, or with respect to small xyz coordinate system is 0. Third dimension is 0. Okay, let us take this advantage of that, and let us say this is the radius r, or the radial location of the satellite. So, now this is the point of satellite, which we are indicating that this is the CG of the satellite. So, let us remove the satellite and talk about the point. So, this is the point indicating the satellite here, red dot. Now, this is the radius. Okay. So, as satellite is moving, this r variable will keep on changing. Here I need to define the position of satellite by one more coordinate, so that I can fix its location anywhere in the orbit. So, this angle, what we call here, it is called true anomaly mu, and that is the location fixing the 2D position of satellite. So, this is the variable that is fixing the 2D location of the satellite in the orbital plane. Now, I can define any position using these 2 variables r and mu in a satellite orbit on this orbital plane. Okay. So, this is my y here. So, I can write r here like this. Well, so this is my eccentricity of the elliptical orbit, which is close to the circular orbit, let us say, or does not matter, it is an elliptical orbit E. So, I am saying that this is the r given by, so now it is representing a position of the satellite. Okay. What about x, which is r here from this point center of earth to this point here? So, this is my r cos mu, you can see Cartesian coordinate system, and this is y, which is the perpendicular distance from x in the small y direction. So, these 2 are already given here. Now, I can express the position of the satellite like this 3 coordinates. Remember, third coordinate is 0, small z axis. Okay, well done. We have defined the position of a satellite in orbital plane. Now, we know that there are two coordinate systems. One is small xyz and another is capital XYZ. And capital XYZ is the WGS84, for example. So I want to bring the coordinates, or I want to measure the coordinates of the satellite using the available information here on the screen into the capital XYZ. That means I have expressed the position of satellite in orbital plane, and now I want to calculate the position of satellite in the capital XYZ system or reference frame. So let us see, we need to do some rotations only. Why? Because both systems are geocentric, and as a result I need not to do any translation there. Their origins are basically coinciding with each other. Their only difference of orientations are there. So let us try to understand what kind of rotation you need. So I can write like this, where my R is rotation matrix, or the xyz of the satellite is equal to R times xy0. Well, first of all, now I will rotate my small xyz system around z axis such that this x axis will be aligned with this line, what we call as with the here blue line, or right now I mark it again, this line here, right. So let us see what kind of rotation we do. This rotation, now it is aligned. Okay. Now what will I do? I have aligned and I have rotated this system about z axis, so there is no change in the z value of the satellite coordinates. Okay. So now just think that if you rotate about this new axis, say x1, right, and it is your new axis called y1, and z is still z. So about x1, if you give another rotation by angle I, remember this omega direction, it is in the clockwise direction, so we have written minus omega. Now you are rotating your new coordinate system x1, y1, z about x1 axis, so that z and y1 will rotate and they will come into the plane of equator by I angle rotation. Let us see. So this is explained like this. This kind of rotation we are doing now. Done. Remember that we have not changed the orbital plane of the satellite, just for the purpose of explanation we are showing it by animation. Okay. So now you have rotated by minus I also about the x axis, which was this, like this kind of rotation you have given, right, and as a result z has aligned with the capital Z. Now still these small are marked here, they are of no use. Okay. This is my new z1 axis, small z1, and this is my y2 axis, or I can call it z2 also, doesn't matter, z2, y2, and x1 is still x1 now. Okay. What else? I have already bring my coordinate system small x, y, z into the equatorial plane. Only I need to give one more rotation, so that this axis, that is x1, will be aligned with the capital X, and this rotation is required here, which is equal to this rotation, and again in the negative direction, because we are going to rotate now about z axis in the clockwise direction. See how do we do it? Like this. So now my x1 axis, which was here earlier, is now aligned with the capital X here after rotation by this angle. So my small xyz system is now completely aligned with the capital XYZ. So whatever coordinates I have transformed now, I can measure this position in the capital XYZ. Again, we have used the logic of coordinate transformation only here, and that's the reason whatever we have talked in module 2 was relevant. Okay, so this is my total rotation matrix here, and now we got, if we place this rotation matrix here and I place these values here, I will get the coordinates of satellite in WGS84 or any geocentric coordinate system or geocentric reference frame. So here I said that it is ITRF, it could be any. So you got how to calculate the position of the satellite in a geocentric coordinate system when it measures something else like r and mu in the orbital plane. Okay. Let us go ahead. So let us have the brief overview of the GNSS now. What is GNSS? Global Navigation Satellite System. or systems. So satellite constellations are, these are the various constellations available and they are countrywide. For example, Navistar, what we call GPS, is navigation, satellite and ranging, and developed by the USA Department of Defense initially for the purpose of military use. However, it is now more popular for the civilians, right? You might be using it, at least in your mobile phone, I am very sure. Because if you have a smartphone like this, right, you are definitely having a GPS inbuilt into that, right? And now you are using for your mobile locations or for your restaurant location or all merrymaking or all your entertainment and so on, or at least for the purpose of navigation in your city. Keep on using it, it's a good facility. Yeah. Second is the GLONASS, that stands for Global Navigation Satellite System, and it is developed by the Russia. Okay. Third is the Galileo, that is developed by the European Union, and that satellite constellation is given the name called Galileo because famous scientist Galileo was from Europe. Perhaps that could be a reason, but yes, its name is Galileo. Thirdly, we have for India that Indian Regional Navigation Satellite System, IRNSS. For Japan, they have Quasi-Zenith Satellite System, and for China, we have BeiDou or COMPASS. Well, these countries have developed their own systems now. Earlier, we have only GPS developed by the USA. Okay. So now, let us look into the next. First is Navistar. Okay, there are minimum 24 satellites. You might be reading this thing again and again. So nowadays, we have 30 satellites in the Navistar or GPS, right? I am trying to update you. You can also read on the internet. All these informations are available on internet also. Well, so these 30 satellites are placed in the 6 MEO orbits at the height of approximately this 20,200, and each orbit is inclined at 55 degrees. So remember, I said that inclination I 55, 55 like this. So there are 6 orbits inclined to the equatorial plane at 55 degrees. Well, and they have different longitudes for this to defining the semi-major axis. So now you can place all these orbits with respect to each other like this, but they are basically inclined towards with respect to the equator of the Earth by 55 degrees. Okay, what about the orbital period? That means each satellite is completing one orbit in half sidereal day. That means each satellite is making 2 orbits in a 1 sidereal day around the Earth, right? That means when it starts from one position, in half a day it completes 1 orbit, in remaining half day it completes 1 more orbit. So again, the point which is here of Earth, that comes 1 sidereal day, it comes back by the time satellites make 2 revolutions around the Earth. That's the meaning here. Okay, what about the footprint of satellite? It creates vertical S shape that we'll talk in next slide, and that is related with somehow this 55 degrees. Then we have this frequency L1, L2. Well, these 2 are already discussed in the basic surveying course. Then we have L5, one more frequency now for the civilian use. They have this codes, CA code, P code, and then we have different combinations of the code and the frequencies which are available for the use or for the receiver to receive it. Okay, so let us go ahead and see what is the vertical S shape. Okay, let us see, this is the shape of the Earth shown here, and somehow if I try to make the 55 degree line, this is 2 lines, that is 55 degree north approximately, and this is 55 degrees south latitude. Okay, so since your satellite is moving in elliptical orbit or in the inclined orbit, so when satellite goes up above equator, it is going to rise on the surface of Earth. That means its footprint or its track on the Earth is going to increase. It will go maximum to 55 degrees, that is inclination of this orbit, and then it will start moving down. So that kind of pattern we should expect on the surface of the Earth, or rather if I draw on the plane, this pattern will be somehow like this, a kind of S pattern, this way and so on. It will keep on repeating. So such tracks are 2 tracks in a day we will have, right? That's the idea here. So that is the meaning of. Next is the Galileo, which is very similar to the GPS, and it has total 30 satellites, and they are placed in 3 orbits of this height, which is slightly above the GPS satellites. And again, the inclination is more or less same, so it is going to create the same more or less same track on the surface of the Earth. That means the track of the satellite will be more or less same as that of the GPS satellites. In each orbit we have 10 satellites, and what is the orbital period? It's written 10 by 1 here, which means they complete 10 orbits in one sidereal day. GPS satellites complete 2 orbits in one sidereal day, but they complete 10 orbits in one sidereal day. Okay. So again, vertical S shape will be created, and then they have 3 signals called E1, which is same as L1. Again they have E5, which is same as L5. Then they have E6, which is different here. Right. So they have 3 frequencies, and these signals, although they are on L1, L5, but they do not interfere with the GPS signals. Okay. So I am not drawing the path vertical S path, which is similar to the GPS. So let us talk about GLONASS for Russia. In this constellation, we have total 24 satellites. They are placed in the 3 orbits almost at this height, 19,100 kilometers, which is different from GPS as well as Galileo. Galileo was slightly higher, or Galileo is slightly higher than the GPS, and GLONASS is slightly lower than the GPS, but all are MEO orbits. Okay, and they are inclined at 66 degree. So you will be surprised why 66 degree, whereas GPS and Galileo they are around 55 degrees or 56 degrees. We'll see the reason. If you just check the latitude of the Russia, which is around 66 degree, or since Russia is very big part, but around we can see the major part of their country, it's around 66 degree. So is it a kind of GPS, or it's a kind of global system, or it's a local system? We call it as a regional system. They are basically targeted or tailored, or basically they are tuned to serve the particular territory on the Earth. So each of these systems what we are talking about now are basically the regional systems, or we can say regional GPS in loose language. Well, go ahead. Okay, I would like to interrupt you here. These are the regional systems, but does it mean that others cannot use, or the people of one region can only use? No, it's not like that. If you are having a receiver which can acquire the data of particular satellite constellation, for example GLONASS or Galileo, you can also use it, no problem. And we'll talk about these things, the specifications of your receiver also, which are very, very relevant to learn in this lecture only. Okay, the next is the orbital period, which is 8 by 17. What does it mean? They finish the 17 orbits and 8 sidereal days. Okay, what's the meaning here? Which is, I can say, almost, since 8 by 17 is, I can say, less than half, or I can say it is, if I take the ratio like this, 17 by 8, so orbital period will be something more than 2, right? So that means they are completing more than 2 orbits in one sidereal day. And that's the reason, in order to give the integer number, we have expressed like this. That means they are covering 17 orbits in 8 sidereal days. So after 8 sidereal days, satellite have completed its 17 orbits around Earth, and again the point where it started above the Earth and the point where it started, both are coinciding after 17 orbits or after 8 sidereal days. That is the meaning here. Okay, what are the frequencies? It uses 14 different frequencies. Remember, GPS is using L1, L5 and L2, 3 frequencies, but they use different frequency. On the other hand, they use only one PRN code. GPS is using 2 or 3 codes, CA code, P code, and maybe Y code also, which is not available for the civilians. It is for military only, but still it is using 3 codes. However, the GLONASS is using only one PRN code, but different frequencies for 24 satellites. And then we have opposite satellites across Earth uses the same frequency. Well, that's the idea here. This is a specification of this system. Okay. Now, if I try to draw the shape, you will be surprised here. Okay. So let us draw the 6th. Yeah, this is the Russia here somewhere. This is Russian part here, territory, right? Okay. So I am removing this right here. So now let us define the 66-degree line. So this is my approximately 66-degree north, and this is 66-degree south. And Russia is somewhere here, as we have shown in this last slide, somewhere here. So let us remove this one. Okay. So now if I try to predict, or if I try to draw the track of the satellite on Earth, it would be something like this, and so on. It will complete 17 such tracks, complete cycles in 8 days, 17 orbits in 8 days. Well, that's the idea here. Okay. Now we have the quasi-zenith satellite system, which is used for the Japan, or developed by the Japan. So it has total 7 satellites, not surprising. Well, it is. So we have 4 geosynchronous satellites and 3 geostationary satellites here over Japan, and 4 satellites are placed in 1 geosynchronous orbit, which is of this eccentricity. Yes, eccentricity is very important because most of the satellites are using almost close to circular orbit, or we can say eccentricity is in the order of 10 to the power minus 3, 0.004, 0.001, something like that. But it has very high eccentricity, and that has very special use here, about especially the drawing the track. We'll see it. Okay. The idea is that Japan is a very small country, and they want to use this QZSS very precisely all around their country, specifically, not around they are not restricting anyone to use it, but still they would like to use it more specifically over their territory, and that's why they have designed their system like that. So it has one orbit of this height, which is since we said it's a geosynchronous or geostationary geo height, and these satellites are inclined at 41, or these orbits are inclined at this degree, 41 degrees, because that is the latitude of the Japan somewhere. Fine. Number of satellites in geosynchronous orbit is 4, and number of satellites in geostationary orbit is 3, that is in the equator plane, that is 0 degree inclination, and there 41 degree inclination of these orbits. Okay. What is orbital period? They orbit one in one sidereal day, one orbit in one sidereal day. What is the footprint? Yes, we'll talk about. It creates kind of small lobe over Japan, and then they have these signals L1C, L1CA, L2C, L5, L6, or LEX. It's also called LEX, that is L1 experimental. They have some different signals, which is slightly different from the GPS, but L1, L2, and L5 are same, right? Again, signals do not interfere. Go ahead. Okay. So let us draw the 41 degree line like this. Okay. Yes, I have changed the looks also, because, and this is 41 degree approximately, or there could be 44 degree, I don't remember exactly now, or let us say it is around 41 degree north, or they are around 44 degree also, could be possible, let us say. Okay. So now if I define a box, because it is creating let us define a box, because the lobe of 8, or 8 figure of the 8 is very, very restricted here, and yes, this axis is also important here. I will show you why. Okay. So here if I draw some figure, so that will be like this kind of 8 over the Japan here, and then it will be big lobe over covering the Australia, part of the Australia, and like this. This kind of 8 shape is satellite is going to create, the track of the satellite, and that's the reason that eccentricity of 0.075 is developed, or it's created, or it is designed that way. Okay. Let us go ahead. Now coming to the Indian Regional Navigation Satellite System. It has total 8 satellites, right? I have taken the recent update from the website of ISRO, and there they have placed 5 geosynchronous satellites and 3 geostationary satellites over India. It has certain longitude where these orbits are there. So these satellites are moving exactly over the particular point on the Indian territory somewhere. Okay. So 5 satellites are placed in the 2 geosynchronous orbits. Well, these all 5 satellites. These are 5 satellites. Okay. So it creates symmetric circular orbit and 2 symmetric figures of 8 as footprint of satellite on Earth, especially around India, not exactly over the India. Okay. So, there are two orbits as we showed here, these two orbits here, and these two orbits are at height of this much and inclined at 29 degree. Again, this is the kind of latitude India has, or most of the part of the India is around this latitude. That is the reason. So, all the systems are now regional GPS or the regional GNSS. Well, still they are global because anyone can use across the world. Okay. So, let us see, these are the 5 satellites, right, and these names are INSS 1A, 1B, 1D, 1E and 1I. In these geostationary orbits, we have 3, 1C, 1F, 1G, 1H is somehow could not be placed, rather it is a kind of lost, or well, it is a failed mission. So, we have total 3. What about the orbital period? We have one sidereal day. So, one orbit in one sidereal day. Remember, it is a geostationary, so it is going to create one orbit in that height of 35,000 kilometers. Well, so we have signals on the S band, which is called 2492 megahertz, and we have also L5. See, it is quite different from the other satellite constellations. Now, if you see, what about the shape of 8? So, let us see, this is the 2 shape of 8s. Why? Because these are the lines of equator, I can say here approximately. Okay. So, these lines which we generally place here, it is 29 degrees north. Similarly, this line is around 29 degree south. Well, okay, now what about the shape of 8? The shape of 8 is created somehow by the satellite tracks in this way. One like this and another is like this. So, these are the shape of the 8 and this is kind of equator position, approximately equator position is this. Okay. So, that is the reason here. So, we are having 2 shape of 8s, that is satellite tracks around India. Last is the BeiDou from or compass, it is developed by the China. So, it has 35 total satellites and we can say here 3 geosynchronous satellites GSO, 5 geostationary and 27 MEO satellites. Okay. So, 5 satellites, these 5 satellites here are placed in 2 orbits. Then it has symmetric circular orbit because its eccentricity is 0.004, which is very close to the circle, or circle has eccentricity of 0. Well, so it creates a symmetric figure of 8 at footprint over China region, and then it has geosatellites, one orbit at a height of this and inclined at 0 degree. Well, that is a geostationary. So, and this is their longitude range. That means over these longitudes, these orbits are placed in the geostationary form. So, satellites are basically moving at some longitude permanently, it will appear like that. So, then orbit of GSO satellites are 3 orbits at this height and inclined at 55 degrees, fine. Now, it has MEO satellites also 3 orbits and the 21,528, which is slightly lower than the GPS, and they are inclined at 55 degrees. Well, what about the orbital period? More than half a sidereal period, more than that. So, 12 hours 53 minutes, almost we can say 13 hours of sidereal day, right, and then it has 3 signal frequencies B1, B2, B3. Okay. So, that is a kind of total introduction about all this thing. These 2 lines which is say 55 degrees north and 55 degrees south. Well, what about the shape? Okay. It will again, let us create the space here. This is the box here, and this bounding box, if I create the shape of 8, so it will be like this. Yeah, it will be, shape will be somehow like this. I am trying to draw appropriate shape. Well, so that is the idea here. So, this is the Chinese region here. So, it is going to serve the Chinese region. So, all these are regional GPS systems, or we can say all are global in nature. However, they are tuned for regional requirements. Now, so this here somewhere it is equator. Okay. Now, we have learned about all the GNSS constellations. So let us try to look into the specifications of GPS receivers that you may buy or you are planning to buy. Okay, so if I have already reviewed couple of specifications of GNSS systems, and I have already reviewed so couple of satellite, couple of GPS manufacturers specifications, and I found that these are very common things: number of channels, position accuracy, data logging rate and data output rate, data storage, data delivery format, data post-processing or the pre-processing, whatever, and then special features. Nowadays they have some special features also, they are provided by the manufacturers in their GPS machines or receiver machines basically. So start with number of channels. Okay, what do you mean by number of channels? If I take the number of satellites, say 30 for GPS, and all these are signals L1CA, L1C, L2C, L2P and L5, right? They are available for the civilians. And now if I say this 1, 2, 3, 4, 5 signals and 30 satellites. So if I multiply the 2, because each satellite is transmitting the signals on these 5 frequencies and code. So they have 30 satellites, we have 5 such signals, so 30 into 5, 150. In the same fashion, if I take these as the number of satellites which are working or which are in the operation, and if I multiply with number of signals each satellite is transmitting, let's say 5 here again, then we will get 120 here. Similarly for Galileo, 30 and 1, 2, 3, 4, 5, 6. So I got something this figure. This could be wrong slightly, right? But there is a purpose to tell you all these things. QZSS 7, then we have something this kind of number. So I got 35. Here 28 satellites for Beidou, then 3 frequencies or 3 signals. So we have total 84 here. And for IRNSS, so far I could not find, or basically IRNSS perhaps not allowed manufacturers to develop the receivers appropriate for the receiving the signals, or they might be having some different plans. But so as on date, these IRNSS are not mentioned in the specifications of the GPS machines or GPS receivers. So if you make the total of this thing, it will come close to 570, just try to calculate it. Okay, now we have the different combinations. Some specifications say 120 channel, some says 220 channels, some says 440 channels, and the maximum is these channels. So perhaps I have shown the calculation for these maximum number of channel. Maybe I could have missed some satellite number, or I could have placed little more satellites and maybe little more signals, whatever. But yes, while you purchase something, at least a GPS receiver of high quality, of geodetic quality or mapping quality, where you expect millimeter level accuracy, you should first ask your vendor what's the meaning of channels. If he is aware of that, he will definitely explain you this calculation. But be sure what you are purchasing, right? Let us go next. DGPS accuracy. What is that? If we use the code based and still we use the DGPS, that is differential global positioning system, that means I have a rover and I have a base. So with respect to base, I am processing the data of the rover. I am processing the data of the 2, but I am calculating the position of the rover. This is my rover, say this pen, with respect to a base which is fixed in location, and rover is moving all around in within some range called 30 kilometers or whatever is specified by the manufacturer of the GPS receiver. Well, so this accuracy in the code based in the DGPS mode is around 0.25 meter. It is not frequency receiver. It is just the accuracy of the code. So that's the meaning here. Okay, what about the accuracy? These accuracies are the local system or are in the geocentric system. All these accuracies of the DGPS or GPS are specified in the geocentric system, not on the local reference frame on the surface of Earth. Be careful on this part. So how can you verify it? We'll see some method today. Okay, what about the RTK performance, real-time kinematic? That means you have a radio modem on the rover and there is a transmitter, radio transmitter on the base, and transmitter is sending, or the base is sending the corrections in the real time to the rover, and rover is finding out its position. Well, in this thing we have some accuracy specified. Okay, further in the static performance, that means I am collecting the data at rover as well as base, and later on I am processing the data in the laboratory after the mission is over. That is, data collection is over, then I am bringing the data of the base as well as rover, and I am processing in the software, and that is called the post-processing. After the mission, I am processing the data, and that is called static performance or the accuracy for the static. They have different. Static is no doubt higher. RTK is also considerably good, because RTK accuracies are in general in the range of 8 mm plus minus some ppm, right? Similarly, static is around now 3 mm to 5 mm somewhere, I can say, and then plus minus some ppm. Okay, so now they have specified also all these accuracies in vertical accuracy form, horizontal accuracy. Accuracy are, as I told, they are in the geocentric coordinate system, not in the local reference frame, so don't get confused. Or the accuracies are not in the map projection system, no, they are in the geocentric coordinate system, capital XYZ, ITRF. Well, sometimes they specified confidence level also, and some of these specifications are saying now 99.9 this kind of confidence level, which means if I draw, let us say there is a true position, I do not know. Now, if I take the position of using GPS machine, I may get this kind of position if I take multiple measurements. Then if I see that, suppose if I take 100 such data, which means that in this given accuracy of 8 mm or 3 mm or whatever, if I draw a circle here like this, 99.9% data or 99.9% of, let us say, 100 samples here or 100 position will be within this 8 mm. Say if I am referring this kind of accuracy, or within this 3 mm whatever. So that is the meaning here. Remember, these accuracies are specified again in geocentric coordinate system, not in the local reference frame. So with respect to the equator, in the equatorial plane, I should measure my planimetric accuracy, and perpendicular to equatorial plane, I should measure my vertical accuracy. Slightly difficult, or slightly imagination is required. Let us go ahead and try to see what's the meaning there. We'll see in this lecture only. Okay, but finally I can say one thing. If you can observe that there is a thumb rule that vertical accuracy is almost 2 times of the horizontal accuracy, and this is the reason. The reason is that since satellite is moving above the equator, below the equator like this, and here it is moving all around, all the satellites. So I have my horizontal positions calculated from all around these positions like this, satellite positions. However, vertical position is always calculated if satellite is above the horizon or above the equator in my hemisphere. Or I can say with respect to my horizon, if satellite is above, then it can be useful for my position calculation. However, a satellite which is below my horizon will not be used. So I can say the half of the satellites are not available to me at a time, but for horizontal positioning, all the satellites are available to me. Or that's the reason people give that vertical accuracy is inferior to the horizontal accuracy, and the ratio is 2 times. So if you have 8 mm, you will observe somehow vertical accuracy will be 15 mm or 16 mm, something like this. Well, let's go ahead. Now, data logging rate. These are the rates are available nowadays in the specifications. That means they are recording 20 data per second, that is 20 hertz, 5 data per second, and you can do this setting while controlling the receiver. Data output rate, they have some different, that means once you take the data from the receiver, at what rate it will be transferred. Now that is not very important, because anyhow you will transfer the data, whether it will take 1 minute or it will take half a second, you will transfer it anyhow. Data storage, they have the internal memory to store the data. That means the moment data is collected, immediately it is stored in the internal memory in the receiver itself. Other arrangement is SD card. You can apply the card. Well, SD card could be a very high capacity, but internal memory is favorable. Why? Because it takes less time to store the data. It's kind of RAM. Internal memory is RAM, and SD card is kind of hard disk that you apply from outside. So transferring the data from the machine to internal memory is much faster than to transfer to SD card. Further, sometimes data delivery format. Okay, once the data is recorded, most of the manufacturers prefer to record in the proprietary format. Why? Because then they will use their software to transfer the data into the universal format called RINEX. So it's kind of developing a proprietariness on their data, or they are saying that we have our proprietary, and you have to purchase the software. But some of the manufacturers are now providing the facility where they are straight away providing the RINEX data in RINEX format. That means you are free to use any free software for data processing. Well, data processing, that data can be processed through software, that means in the post-processing manner, or it can be processed in the hardware also. These facilities are also available. That means whatever data you are collecting, it is directly processed immediately there itself in the hardware of GPS receiver itself. And once you take the data out, it is delivered you in the direct answer form. So there are some special features. First is the battery. Batteries, nowadays they have hot swappable batteries, which means there are two batteries in place, but one battery at a time can be charged and one battery will be in service. So now you realize, let's say you place two batteries, both are working. So one battery is being used by the GPS receiver and one is a spare in the box itself, in the receiver itself. Now the moment that particular battery which is being used is discharged, it will give you an indication. So what will you do now? You will remove this battery and automatically receiver starts using the another battery. Okay, what's the advantage? Now you can charge this battery which you have removed, and then once after 2 hours it is charged, again you replace this battery and you can check the status of the another battery which is being used. So this feature is called hot swappable batteries. Okay, what about data transfer? Data transfer can be done by Bluetooth or even with your helping GSM. GSM modem means you can put a SIM there inside the GPS receiver, and using that SIM it can communicate to your mobile, or you can transfer by email also, right? So that's somehow an advantage now. What about the radio modem? They have internal radio modem as well as external radio modem. For external radio modem, you need to pay a little extra. Nowadays, internal modems are also coming for RTK facility. But remember, in India, transmitting the frequencies, or especially radio frequencies, are denied. Then we have facility called tilt sensor. This tilt sensor means, suppose you are using the GPS or the DGPS on your boat, and boat is moving on a water surface, definitely it is moved like that. So it is kind of tilt is there. So this tilt sensor make the measurement of tilt, and it will provide you the tilt correction. So if you read this tilt sensor, understand that is the purpose. Then we have operating temperature. Generally they specify minimum to maximum, while these days range is somehow around -20 degree or maybe -30 degree to +55 degrees centigrade. That means you can go in desert where temperature could rise around 50 degrees and you can work with your DGPS machine, or you can go to the glaciers where temperature is sub-zero, even up to -10 degrees centigrade or -20 degrees centigrade, your GPS machine will work there. Okay. So what about the accuracy? Suppose you have ordered one DGPS and you want to verify your accuracy. So what will you do now? Idea is very simple. So we have devised a simple way, rather we are suggesting. So let us say there is a line AB, and now you will collect the position using your DGPS or GPS over these points. Let us say 10 points you have placed like this. Okay. If you calculate your position which is given by the DGPS, that means you have placed your DGPS machine here, here, and so on. Then you will calculate the position. Let's say these positions are like this, right? So what will you do now? You will first take an arbitrary position, say this by your DGPS, say this is your reference point, bring your coordinate system from geocentric coordinate system to the local terrestrial frame. That means you put, let us say this is your x0, y0, z0 coordinate with the help of DGPS. Then what do? You assume that this location which you do not know truly, but you say that this is an arbitrary position and I am making my arbitrary reference frame. Okay. Now let us say this is my x1, y1, z1 position, fine. Okay. So you can find out difference, that means what is the length of this vector like this. Okay. Similarly, you can find out from this position where you can put total station here now, what is this location of green dot, and try to find out the accuracy between the two, red dot and green dot. right? So that is calculated by GPS or DGPS, and that is position is calculated by your total station in the same reference frame. Remember, you will orient your total station in the local terrestrial frame, and local terrestrial frame is designed with the help of this point. You can also do one thing, you can take another point here and then you can find out the bearing of this line, and by measuring the bearing of this line, let us say x0 dash, y0 dash, z0 dash, you will use this line for the referencing of your total station. Again, what about the quality? Use error propagation, use adjustment computation to find out the quality, and this is very easy logic here. You find out all these accuracies like this, or maybe this accuracy, and then you can find out whatever specifications are there or whatever requirements you have about accuracy, whether these accuracy figures are fulfilling those requirements or not. Well, that is the idea here. Now, you can use the RMSE calculation also, that is, one is reference and one is observed. So, this is your observed, and position of this by total station, which is let us say 3 mm accurate, it is your becomes reference. So, now you do reference minus observed, and if there are n number of points, then you use this formula to find out the RMSE and check whether whatever claim has been made by the manufacturer are true or not. I hope that this lecture was very informative for you, and there I would like to recommend, if you want to read more on the applications of the GPS, then you can go through these 2 papers and report. They are available free on the internet, and you will be enormously benefited if you go through these 2. So, we will meet in the next module on photogrammetry in next lecture. Thank you very much.